Grazie. Okay. So let's start with a little bit of review, what we did so far. So the first important thing is that we have a function which gives a value to every set. Okay? So it is m star for every set E. A is equal to the infimum to the sum of the length of intervals, or this is the measure of open set at the end, such that A is contained in the union of these intervals, open intervals. Okay. So the properties are it is monotone and subadditive, and to the empty set it gives 0. So the second is that now we need to define what is now the measurable set. Remember we defined that, so this is the outer measure. And instead of having subadditivity, we need to have additivity. Okay, so after trying trial and errors, at the end you arrive at this definition. E is measurable, and we call it with M, which is the Lebesgue. Measurable, simply because the length of interval is the length. Otherwise, I can have some other function of intervals, and then I can repeat the construction. What I get is something, well, the construction is purely formal, but you get something else, no? But still okay, still a measure and still a sigma algebra. Okay? So if m star of A is equal to m star A E plus m star A minus E. So it is additive with respect to E. And then what we have proved is that with this definition, M is a sigma algebra. And it contains the open set. So it contains the Borel sigma algebra. Which is the smallest sigma algebra which contains the open set, the topology. Okay. So after we have this very nice thing, we proved also that the set in M are not that bad. Well, a priori, this is a completely theoretical construction, and okay, you know you have this M, you know which are the Borel set, because you can construct in another way, but still can be something arbitrary, and then you have this theorem, remember, which is the regularity. This is very important. So if E is in M, then there exists, let's say, open, so this is equivalent to exist open, such that, say, the outer measure, well, open containing E, and the outer measure of open minus E is less than epsilon, and this is equivalent to there exists a G delta G. G delta G containing E, and the outer measure of G minus E is equal to 0. So that we can rephrase this regularity. Then okay, we have the same part from inside, no? Then same, let's write here, same from inside with closed set. So essentially this theorem is very important because it tells you that M differs only from the Borel sigma algebra just for set of measure 0. Okay? So the only, say, freedom you have is in these sets. Okay. So far for the sigma algebra, and now we need the measure. Okay? So we know already what it would be the measure. So this is the radio, and now we have the Lebesgue measure. So after this construction, you know the Lebesgue measure will be, I mean, I did everything, just the outer measure restricted to the measurable sets, no? There is no... is equal, so the definition is M star restricted to the measurable sets. So M star is defined everywhere for every subset, and then you restrict to the measurable sets. And what you want to say is that, well, this thing over here is a measure. Just I'm looking now at my notes, I forgot, because so this is the notation of the book, but actually is non-standard in my opinion. Because, well, the M refers to the measurability. Actually, indeed, I switch in my note because usually I have another notation. It usually is L. So it's with a capital L, okay, but we stick with this guy. So if you will forgive me, sometimes for some reason I change with this M with L. L is Lebesgue measurable sets, so I refer to the Lebesgue. Because what is important is that the measurable, so you see from this theorem that essentially the M, so okay, I will open a little bit of parenthesis here. So as I said, you can start with any outer measure, not just the Lebesgue outer measure, and repeat the construction. You get something else here. So but actually in many cases, there is also a theorem which tells you which are the cases, and actually in one of the exercise, we have essentially that construction. When we say that if two sets have a positive distance, then the outer measures are additive in that case. You remember, no? And so this is a property, is the Karateod reconstruction of measures, which constructs measures which are defined on the Borel sigma algebra. And this holds still for the measures. So the difference is the sets of measure 0. So if you have different measures defined and sigma algebra, which contain the Borel sigma algebra, so where this thing can differ? Where can this thing differ? Only in set of measures. So what happens is essentially that some set which have measure 0 with respect to our M star, they have not measure 0 for another thing. It seems a little bit, but this is, I mean, okay, I'm saying something that, well, I hope somebody will get it, some other they need some more time to think, but okay, so the construction is theoretical, and also this is still okay, but since M star, they differ, if you start with two different M stars, then what happens is that the set of measures 0 are different. And this means that this sigma, they are different. So let's go. So what now we need to prove in order M to be a measure? This is a question. Sorry. The two properties, no? M of 0 is 0. So n of the empty set. So one is the m of the empty set is equal to 0. A countable additivity, yes. Measure of the union of this joint is the sum of the measure of the EI. Okay, what about the first?
Prove it because it's M star.
Yeah, exactly. M star is 0. Actually, we have even something better. We know that the measure of intervals is the length. You remember? So, I mean, we know that even sets which are countable have measure 0. So we need to prove the second. So just to proof of sigma additivity. And now, of course, we have to prove one side. No? You remember, one is automatic from the fact that this guy is subadditive. So we need to prove the other side, that it's additive. Okay, so let's start. The starting point is that we proved another property, if you remember. So if you have two disjoint sets, you remember we proved that M star, well, it was a corollary of the fact we need to prove that this guy is a sigma algebra, no? So we need to prove that countable union satisfy the same property here. But first we prove it for disjoint. Well, we prove even not disjoint, but for disjoint it takes a very nice thing. Okay, you remember it was something like this. A intersection the union of disjoint, finitely many disjoint sets is equal to, okay. So now you apply the definition which each set EI. And now A minus the set EI, okay, it's just the intersection with the remaining one, no? And A intersection EI, so you keep it. So I will just write the final thing. You recall this formula from last time? Otherwise we do that. Because it's very nice. Okay, let's do that. So it's okay if it's just for 2. Yeah, it's fine. E1 is measurable. So A intersection E1 union E2 intersection E1 is just A intersection E1. And what is left is A intersection E1 union E2 minus E1, and what is left is just, since they are disjoint, it's one line. Is that okay? Okay, so now we have this formula, and now, I use the additivity in some sense, and now let's prove the sigma additivity. So let's apply now to the union. So this is a mistake. So for A equal to R, for example, the whole set, now this is measurable, so I get M of the union, finitely many, is equal to the sum of the union of each set. Just application.
Additivity in finite case only.
Yeah, just finite case. And now how to pass to the limit. It's easy because we have just one inequality. Okay, so we need to have the other one, no? Okay, so let's enlarge this set. What is the natural enlargement? Look at this guy. There are only few sets on the blackboard.
All the union.
The union. The whole union, no? So this is greater or equal than the measure, so less or equal than the measure of the union up to infinity of I. Monotonicity, and then the formula I just used. And now, take the limit, is the definition of the sum, is the limit of this guy. So, taking n to infinity, I get that the measure of the union of I is greater or equal than the sum of the measure of I, and this was the only part I have to prove. Subadditivity for the other inequality. Okay. Conclusion, finally we have that this is a measure, and now we have everything is settled. No? And let me state again, this is not, okay, even if some steps are arbitrary, I mean not arbitrary, are theoretical, because we assume that, okay, I need to check this guy with uncountably well. This is the power set of R, so it's even something which is not even continuous. It's a power which is larger than continuous. So this is completely impossible for a human being to check it, but actually this is possible. So you're allowed to do countably many operations. This is possible. So we have something that says, take the Lebesgue algebra, just add the set of measure 0, which are sets which live between a G delta set and an F sigma set. These are your measurable set. And finally, for that, you give M star or M to those sets is equal to M star of G. So essentially, you are measuring the G delta set. And then you know that is a sigma. So it's a constructive way.
So the set of Lebesgue measurable set is has the power of continuum only. It's by projection with R.
No.
It's larger.
It's larger because we have the 0 sets.
When we add the 0 sets.
Yes, the border sets is just the continuum.
Okay.
But the other is larger. You have the subset of a set of measure 0, which is uncountable. And now we are going to construct these strange sets. Okay. Okay, now we do something. So everything seems again. Is really seems very basic, but it's really powerful. And now we see another result, which is seems so stupid, but actually instead is the basic of almost all the limit. Well, I should say all limit theorems. Passage to the limits. Let me see how I state it. Okay, yes. Theorem. This is the monotonicity, monotone convergence. It's actually usually not referred as monotone convergence. Usually monotone convergence refers to function, but actually this is, you will see, is the same. So the first part is that if EI is a sequence of Lebesgue measurable set such that, okay, let's say increasing, which means that EI is contained in EI plus 1. Then I'm curious about the measure of the union of EI, which is measurable because of the sigma algebra. Well, it turns out that this is the limit of the measures. Of the measure of EI. So if the opposite EI as before in M is decreasing, and measure of E1 is less than infinity, then the measure of the intersection is again the limit. Let's leave this one here. It's not needed. This we can leave it. Okay, proof of the first. I'm just using what is written there. So first suggestion you should get is that this limit would become the limit of the sum. Because the sum there is a sum to infinity, so it's the limit of partial sums by definition. So that would become a limit of a partial sum. So the second suggestion I give to you is that suppose that, forget about the inclusion, suppose that the sets are disjoint. And now the statement is that measure of the union is the limit of the sum of the sets. So it's already there, no? It's property 2. Okay. So let me write. By 2, I have that the measure of E of the union, let's say, the union of E is equal to. So I want to write this union as a union of disjoint sets.
Yeah, we take E I plus 1 minus E I.
Exactly.
Union.
Then we need also U1.
Yeah.
Are these set disjoint? Yes. So this is the sum of the measure of, let's say, so should be a measure of U1 plus the sum up to infinity of the measure of E I plus 1 minus U E I. This is E1 something. And now, this is not exactly what is written there. The sum is by definition the limit of partial sums. So it's the limit over n. Okay, here I use I, so let's say I should be n. Let's change it n. And I'm computing in measure of E1 plus measure of E2 minus E1 plus up to, if I fix n, is the measure of En plus 1 minus En. Now the additivity, partial sum additivity. So this is E1, E2, this one is included in the other, at the end this is the limit over n of the measure En plus 1, which is the state. Okay? Now, second part, I need just this. the complement, but you cheated because you say you know already the theory. Yeah, the complement. So why do I need this guy?
To avoid indeterminate
To avoid, because the problem is that if I use the complement, I'm going to write, so let's say apply to part 2, I apply to E1 minus EI. So this is a family of increasing sets. Because EI is decreasing, no? So from the statement, I get M of E1 minus, okay. So this is the union of E1 minus EI is equal to the limit over I, the measure of E1 minus EI. Now, okay, this guy is the measure of E1 minus the intersection of EI, no? I should be smart, I have been smart and taking 0 because the my 1 seems an I. Okay, so this is just the statement, this is just the theory, and now what I say is that this guy is the measure of U1 minus the measure of that guy if the sum is meaningful. So this is measure of U1 minus the measure of the intersection if at least one of the two is finite, otherwise is indeterminate. And then I have measure of U1, because the limit is a constant, minus the limit measure of EI. Okay? And now if measure of D1 is not plus infinity, I can cancel. If less than infinity. Let's go on with some nice definition.
It's still odd if there is I such that the measure of EI is finite.
Just one, yes, of course. You start from that I. You need just to start from that I, because they do not depend if you fix them. Okay, so we keep this theorem, and now we do another thing. Do you have this week the tutorial or not? Ah, okay. So I will give him some exercise to do in class. I hope to be able to show you the Hausdorff measure. Okay, definition. So this is the definition is really important because every time you say, and this is one of the powerful property of measure theory, is that you can state something up to a set of measure 0. So a property holds, so is said to hold Lebesgue almost everywhere. Or almost every respect to the Lebesgue measure. So this is almost everywhere. If there exists n is a set contained in R such that the measure of n is equal to 0 and the property holds outside n.
N is measurable.
0. I can put M star, but I know that set of M star is our measure, so I have no trouble in that. So let's see the first property, and this is an important inequality at the end. It's called the generalizer of this guy is the Chebyshev inequality. We will try to do the statement as in the book, and then I ask you to generalize it to the Chebyshev. Assume that EI is a sequence in M, so measurable set, such that the sum of the measure of EI is less than infinity. Define. Okay, the statement is very ugly because I should put something. This is not the way to write statement, but f of x is equal the number of I such that x belongs to EI, which is equal to the sum, the indicator function of EI evaluated in x, by definition. Then f of x is less than infinity almost everywhere. So let's see first the proof, and then I ask you to generalize. Okay, and I want to ask you if you have any idea how to prove that.
By absolute contradiction.
By contradiction, yeah, how to do that by contradiction?
If we suppose the converse, it means that there is a subset of E which has a non-zero measure, such that f of x is infinity for all elements of this set. And so this f is included in infinitely many EI, right?
Which can be different for any x.
Yes, but I mean each EI has there is infinitely elements of the collection.
Each EI, you would
not all EI, but infinitely many.
So
EI.
for any x, so let's say you have a. Let's follow. So let's assume A is contained in the set where f of x is equal to plus infinity.
Yeah, and the measure of A is not zero.
Okay, this we can assume later. But
Yeah.
let's say negative in 0.
Yeah. The first assumption, what it means, that A included in that set, it means that there is infinitely many.
You're saying the following. Wait, you're saying for every x there exists a sequence I 1x,
Yeah.
I 2x,
Yeah.
which is infinite sequence.
Yeah. So that x is in all the
Yeah.
set, and that's by this. Yeah. So when we change the x, the indices may change, of course.
When you change A, yes,
Yeah. So
that's the problem.
Yeah. So
You cannot say that you have infinitely many EI which contains A.
Yeah. I got it.
You see. Okay, so let me give you the suggestion. Then we think, or I suggest how to do the generalization. Okay, but the idea is not bad. Okay, I cancel, but actually is the same. So define. So if you have countably many sets, certainly, let A, as you said, f of x equal to plus infinity. Certainly, A is contained in a union from I equal to k to plus infinity of EI for every k. Is that true? Yeah, essentially it's what you wrote, but I just observed that I don't need there is a family which contains all A, because I have the sum. What I need is just that at least everybody contains a piece and the sum diverge.
Yeah.
That's to be sure that everything contains a piece, I have to use the additivity. It cannot be A to be completely. So since I have counted many EI, at least one EI contains a piece of A. And this is the idea. So certainly A is contained in that set because A has infinitely many I, and so certainly for any x there is one I inside this one. There is one I larger than k, and so there exists one x inside. Now, what is the measure of A? By monotonicity, the union, okay, and by subadditivity, the sum. So essentially, or I can also state, well, now this guy, the limit for k of this guy is 0 because the sum converges. So I deduce that M of A is equal to 0. Because this can be arbitrarily small. And now, it's not in the textbook, but I would like you to think a little bit about the generalization. So, and to do that, allow me to switch a little bit to the integral, because so far we have very little tools. So, this function is the sum of this guy. So, let me say that the integral of this function is the sum of the integral of this guy. And so I have the integral of f. This is not correct because we don't have the tools. I mean, it's correct, but I'm applying something that we are going to prove a few lessons ago. So let's see this is a proof in the future. But I prefer you to learn this inequality. Is equal to the sum of the measure of EI. And now I do a drawing. Just I want to see if you understand what. So this is a strange function, and I want to compute what is the set where f of x is larger than some constant a. What do you think? My question is, I want to compute the measure where f of x is larger than a. I mean, we don't have still the Lebesgue integral. Assume we haven't used the Riemann tools. So I'm telling you, you can compute essentially the integral of almost every function. And you have the tools like the Riemann integral, and you know this formula here. Okay, so let's multiply this by a. So what this number represents in the picture? What is
the
number?
area of the rectangle.
Do you agree? Because this A is A and this is the set. Okay, so which inequality now I can see?
It's less or equal than the integral.
Than the sum. Okay? So which inequality now I deduce? The measure where f of x is larger than a is less or equal than the sum divided by a. If a is plus infinity, it's 0. And this is the Chebyshev inequality. It's a trivial inequality, of course. But at least you understand that this lemma is really a particular case of the Chebyshev. Okay. So far so good, and now some exercise, at least just to warm up. Well, the first thing that I hope you ask you is, in the theorem about the monotone convergence, what happens if I have a set which I have measured infinity and they shrink to another set? Why is not in the assumption I need to assume that the first set has measured less than plus infinity? So actually, are there questions about this picture? It's natural. You have really, trust me, this is one of the most important. You use this in your daily mathematician life because it's really powerful. I mean, it seems stupid, but actually, it's really powerful because sometimes it's much easier to estimate an integral than to estimate a set. Okay, some exercise. Show that there exists, let's say, a family of EI decreasing, EI measurable decreasing, such that the measure of the intersection is less than the limit of the measure. And to be honest with you, I mean, there is a generalization, because many of these statements, they become statements for integrals, no? Because you think that essentially the measure of a set is the integral of the characteristic function. So at the end, we have statements which are the translation of these statements into integrals. So it seems trivial, but actually is not. It's really the basement of all the theory. So you have any idea here? First of all, they should have measure infinity.
Can take the interval from I to...
Yeah, you know. So I is the interval I plus infinity. The section is empty, but clearly on the left-hand side you have plus infinity, so the worst case, no, in some sense. I don't need to go on. Do I need to go on, or you understand how to end up after this choice? Well, you try, but it's not done. Oh, and now, since I have the tutorial, I will not spend too much time here, I give the answer. And now the important question which remains, in my opinion, is, also the opinion of the book, of course, is the existence of a non-measurable set. How many are they, and do they exist or not? If they don't exist, why I should do all this stuff? So all the constructions are based on the same method, but you can change the parameters and you have different stuff, of course. And then you have transformation of the measurable sets, which are non-measurables, and whatever you want. So I do the easiest construction, in my opinion. So construction of a non-measurable set. And now I ask you, clearly I know the answer, but then after a while you digest even stones. So, which would be the property, well, in order to show that it's non-measurable, I should say, if it is measurable, I get a contradiction. Because I cannot taste for it's difficult to find a set such that the outer measure, even computing the outer measure, it's difficult unless you are intervals, and then the theory tells you that essentially you need only intervals and open sets. But so which property for you would be a problem? The monotonicity is okay, because outer measure are mono. So I need to prove that it's not additive, it's the additivity.
Yeah,
The additivity. And how to prove that something cannot be additive?
by contrast.
Of course, I need to contradict something, but so let's. Monotonicity is okay.
No, I mean, if we assume additivity, we will get
But
contradictory inequality.
monotonicity, I mean, the whole theory is that monotonicity is granted.
Yeah. No. I mean, when we assume additivity, then when we apply the monotonicity, we will get a wrong inequality, like 4 less than 3 or something.
I don't know if you can do that. I think, well, at least what we follow now is the fact that if I construct a set, I construct, let's say, how many? I want to assume, I want to prove that cannot be additive. So I construct countably many sets. And if they were additive, I would get a contradiction. So the idea is that assume I can partition the interval 0, 1 into countably many sets that have the same, that actually are the same. They have the same outer measure. Okay? Then, if they are measurable, I get that 1 is the sum of countably many sets which have the same value. This is impossible, because then they should be 0, but then the sum of 0 by sigma additivity is 0. On the other hand, if they are not 0, it's plus infinity. So the idea is this one, because, and so I should tell that the only one I know. I mean, you have different recipes, but actually you go to the bottom is always this one. And I think there is also in logic a result which tells you that this is the basic, the only construction. So everything is equivalent to this one. So the idea, partition 0, 1 into countably many sets with the same outer measure. Countably many disjoint sets. Okay, if I can do that, it's done. Then they cannot be measured. Simply because if they were, then 1 is the sum of the measure of this set AI, let's call this set AI, but then they are the same. So if M of EI is equal to 0, then 1 is equal to 0. If measure of AI is greater than C, greater than 0, then 1 equal to infinity. There is no choice. Okay, so let's do that. So essentially I construct a set. So I've made let me do that. So essentially what happened is that my set will be one that translated on the other. And at most I take a piece and I move back. So translation is invariant for M star. If I cut, remember that the intervals are measurables. So if I cut a non-measurable set, the measure of the measurable set is the sum of the two pieces. If I take this one, move it back, the measure does not change. Okay? So this will be the operation. And now, if you think I have countably many of these sets, essentially what happened is that I suppose one is the translation of the other. So if I take one point in this guy, let's assume I fix one point. When I translate it, I get another point. If I make them equivalent, I have a class of equivalents which are made by countably many sets. Okay? So essentially, I need the construction is that I need, first I build partition of 0, 1 into equivalent classes made of countably many points. And then the AI will be a selection. I take one point in each class. So, construction. 1, define x is equivalent to x prime if x minus x prime is equal to, let's say, 0 modulus, sorry, it is equal to alpha n, let's move it to alpha z modulus 1. Okay, so I'll just say what is that. Alpha belongs to R minus Q. 0, 1 minus Q, doesn't matter because I have 0, 1. So let's say this is alpha. So this is x plus x prime equal to x plus alpha modulus 1. Okay. So how to build the equivalent class is written down there. So give me x. This x prime, which is x plus alpha, is in the class. And then I can take 2. This is in the class. Essentially, what I'm following is the orbit of this point. Also in the past, no? Okay, here, you get here, and so on. So, how many points I have in this class? Because can I have finitely or infinitely? Is infinite because? Why? Because it's irrational. I never close the cycle because there exists no n here such that alpha n is integer. To be closed means that the difference is integer because modulus 1. Okay, so we say that we call it Cx is the equivalent class. So it's the equivalence class, let's say Ex is the, Ex is the equivalent class for X. So I'm partitioning, or essentially I say that I'm partitioning the union of Cx is equal to the interval 0, 1. Okay. Now what I do is that I want to take, so I have a partition into equivalent classes. How many equivalent classes do I have? countable simply because they are countable and 0, 1 is uncountable. So I have the power of continuum. So now I take a selection. Let A is a set such that is contained in the power set of R, such that for each Cx, the number, the cardinality of the intersection is equal to 1 point, let's say, okay, here I need some notation, let's say is 1. So I take a set such that it selects 1 point in each class. Can I do that? So because, okay, this is okay. I mean, I can compute it. Take, this is like x plus alpha z modulus 1, which is computable. Can I do that? Not so. The answer is that yes, if you allow me to. No, if you don't allow me to. So here, the axiom of choice enters. So this is really important. This is the axiom of choice. I have a choice function which gives me to every set 1 point. If you don't allow the user me to use the axiom of choice, then the construction stops here, which means that you don't know, you cannot answer the question, is there a non-measurable set? Okay? Okay, now we have this set A. I want to say that A plus alpha z, so first alpha, let's give any integer z, intersection A, sorry, modulus 1, let's say this, modulus 1, intersection A is equal to the empty set. This operation is that you take A, you translate it, cut one p set, move it back, because it's the modulus 1, and you never get back to A unless z, sorry, minus z, of course. Why is that so? Okay, assume that I have a 1 point in this A such that it coincides to another point in A plus alpha times an integer modulus 1. Look here. Then A is not a choice function, because then A has 2 points now for that particular x. Because it has x, and then it's translated. I know that is something strange, but unfortunately, as I said, this is the only construction human beings have to do this thing. So far we have, so let's go back to the first part, to the blackboard here. So which point we are now? We are sets AI, disjoint, and what happened is that the translation of each set, so each new set is the translation of the other. Okay? So I can write now which are my sets. My sets, I is equal to A plus alpha I in Z modulus 1. So this set are disjoint because of this property. Are countably many because I in Z. And they have the same outer measure, yes, because it's the translation. Outer measure is measure invariant. So let's consider the operation modulus 1. Operation modulus 1, you cut and move back. cutting an interval of measure of, since the interval is measured, the sum of these two pieces is equal to the outer measure of the set of the whole set, moving back. And then the union is again the cutting operation. So I have counted many disjoint set with the same outer measure. Conclusion, they cannot be measured. Question? Yeah, I know it seems a little bit strange, but it's definitely this. Please ask, because there are other constructions, of course.
How we say they cannot be measured?
Because it's this part. Assume I partition 0, 1 into counter-remaining disjoint set with the same outer measure. And assume they are measured. The outer measure coincides to the measure. So now I have, since they are measurable and they are disjoint, the measure of 0, 1 is the sum of their measure. This is the additivity. And now, what is the measure of these sets? If it is positive, then this sum is plus infinity. They are counter remaining. And so I get contradiction, 1 equal to plus infinity. If they are 0, again additivity is the sum of 0 sets. So 1 equal to 0. So if I can do this construction, then if I find counter remaining set as above, they cannot be measured. At least one cannot be measured. Here, since they are translation one of each other, they are not measurable. So, let me ask you a question. Is the intersection of this particular class of sets, if I intersect with a measurable set contained in 0, 1 with positive measure, can they be measurable?
I mean, if the union of non-measurable set is measurable.
No. I take now, so this is an exercise. Let's say, an interval I contained in 0, 1. Interval.
Interval.
Yeah.
Okay.
Can it be that one of these AIs are just A, essentially, because one is the translation of the other? Say that the length of I is greater than 0, of course, otherwise, yes. Okay, I let you think. The answer is no. They are so bad, but the answer is no because of the construction. You cannot say for general non-measurable set, of course. But because of the construction, you see the construction is completely invariant. So essentially you can take this interval here, and then what happens is that more or less what you are doing is just restricting the construction to a subinterval. So we want that. Okay, now today is the day of strange sets. So now we go a little bit forward and we construct very strange, the Cantor set. The Cantor set are very important because are set of measure 0, but they have a lot of properties. And inside this set of measure 0, essentially they show that you can put the whole R. So all the structure we have in R can be restricted to a set of measure 0. So there is a lot of space.
In the sense of topology? Or?
In the sense of topology, well, you have to remove the continuity. because the set is sets we're going to construct, they are totally disconnected. But from the point of view of, well, if you allow the maps not to be continuous, homeomorphisms, but you allow them to be Borel maps on one side and the other, yes, then yes. In fact, the isomorphism of matrix spaces is for Borel maps. You cannot say for, because you lose the connection. Okay, this is a close out. In any case, you will see that you cannot say, it cannot be homeomorphic, of course. You can preserve continuity from one side, but not from the other. Because the disconnect, if you have something disconnected, the function is continuous, of course, because there is no connection. This is trivial. Okay, so the construction of a Cantor set. Okay, let's do it graphically, because then we can write the formulas. So now I start with this function here. The identity restricted to 0, 1. So my operation, the Cantor set usually are constructed by you give a family of self-similarities and you apply that to subset of the function. Or the set that you're considering. No? You have some transformation, and then that transform one part into another one. Then you distribute everything and apply different pieces, and you get these very nice looking sets that multiples or whatever. So here we do the easy case. So whenever I have a line, I divided the interval. So I have a straight line. I divided the interval here into 3 parts of the same length. So in this case, it would be 1/3, 2/3. I divide the range into 2 parts, so here will be 1/2. And I replace this line with just the first line which goes to 1/2. Here is constant. And then the second line which goes to 1. It's a transformation. I declare that this is my transformation D. The next step, I need to call chores today, but of course I don't have. I redo the construction here. Can you tell me what I do now? And so you rescale everything, so I need to repeat the construction into this interval.
1/9, 2/9.
Yes, I divide by 3. Now it's 1/9 to 9.
1/4.
I divide it by 2. What I do here? 1. So now it will be 7, 8, 9. And this will be 3/4. And I replace. So now to which interval I apply again the transformation? Well, I can apply to all, but clearly it's invariant in these intervals. To which interval I am applying? Here, 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 here. So at the end I have 1/8. I will try to make it bold. This one. This one. And this one. And then I'm going on here. So this way, in this way, you construct a family of continuous. Okay. There are doubts about the continuity of the family. I replace a continuous piece with a continuous piece. Increasing. Doubt about increasing? It's increasing. Clear. From 0, 1 to 0, 1. So on to 0, 1. You have to imagine that I repeated the construction, not writing the transformation. I can write the formula, but you can do by exercise with the formula. But just to look what happened, no? It's clearly always maps 0, 1, 0, 1 functions. Okay, for you? So clearly what I'm interested, since we are in analysis, to take limits. If it exists. This is called the Vitali function, or Cantor-Vitali function, let's say. Of course, for what we are going to prove, Cantor should appear, because you have these very strange sets that they behave like they should not. Okay. So let's prove that it converges. Let's see what we say. So what is the difference between, let's say, Fi Fi plus 1 minus Fi in norm C0? How much is the difference? Start. What is the first difference? Is this quantity here, which is of the order of certainly less than 1/2. Do you agree in that? The difference of the second one is certainly less than 1/4. Yeah, because at most I touch the function into rectangles which have height 1/4. So the next one will be 1/8. So at the end that this guy is less or equal than, okay, doesn't matter, 2 to the minus 5. Does that mean that Fi is converging?
Converging uniformly?
Yes, it's 0.
Yes.
Yes, because I just apply the definition, no? And the triangle inequality. The norm of Fn plus k minus Fn is less or equal than the sum from n plus 1 to k, Fi plus 1 minus n plus k minus 1. And it's less or equal, okay, let's say this guy is 2 to the minus n. And that's 0, so it's a Cauchy sequence. It's 0, and then Fi converges to a unique phi, and the uniform convergence preserves the continuity, which is continuous. The pointwise converges, so the increasing, but if something is increasing and converges pointwise, the inequality is present. On by pointwise converges, so it is increasing. Well, if everyone is 1 for all, that stays the same. So phi of 0, 1 is equal to 0, 1. Okay. So now the other name of this function is David's staircase. and now I will try to draw a little bit the function, and I hope you understand why it has this very nice name. So if you draw the function, essentially what happens? The function is constant in the union of all these intervals. So 1/3, so this interval here, plus this interval here, plus some pieces here. So the function, because phi is not be touched, so we coincide to the constant here. I never touch fi once I reach one of these flat parts. So phi is constant. So as zero derivative, whatever. We cannot say the derivative because later we will compute what is the derivative. But so far, in the intervals, in the set, the union, so let's say 1/3, let's take the 1/3, 2/3, union 1/9, 2/9, union 1/7/9, 8/9, union, what the next would be 1/27, 2/27, and so on. So what is the measure of this set? Okay, this set is 1/3, plus this set are 2/9, plus the other you have 4 sets of length 27. The next step you have 8 sets of length 81. So this is the sum. Okay, I collect 1/3, 2/3 to the I, from I equal to 0. And if you do a computation, this is equal to 1. Okay, so this is a strange function. It means that I have all these intervals here. Okay, and the function is flat. Now, why I call it Devil's staircase now?
What?
Devil's staircase. So it's a very strange stair, no? I mean, the space of each step is 0. So you don't have space because everything is covered by flat parts. So the space of thing going up is 0, but actually at the end, since you have uncountably many of them, you reach 1. You see their contradiction. So essentially, the function is continuous, or you can think the function is continuous. I don't have any step. But instead, I have something which is an infinitesimal steps, and well, it would be nice to that. You don't even feel it, but at the end, you arrive to the top of the mountain.
Probably that it's not differentiable at all this.
Yeah, of course. We can, the derivative of this function can be computed. We will see later the ISA-BV bounded variation function, then we can compute it as a measure. And this will be another measure. So the derivative of this function is a measure which is not the Lebesgue measure, but the theory will apply. Okay, so I think we stop here, and that's it. So when we have the tutorial,